Hello, Accelerated Chemistry students. This is Mr. Spurk, and this is your Chapter 14, Section 2 notes all over the gas laws. So these gas laws are going to be named after the scientists who discovered them. So first up, we have Boyle's Law. If the temperature is constant, as the pressure of a gas increases, the volume decreases. And on the other hand, as the pressure decreases, the volume increases. So Boyle's law states that for a given mass of a gas at constant temperature, the volume of a gas varies inversely with the pressure. So what we can kind of say is as pressure increases, volume's going to decrease, and vice versa. If pressure decreases, volume is going to increase. So we represent that mathematically since this is an inverse relationship. So we have P1 times V1 equals P2 times V2. And that P1 and V1 just means our conditions before the change, and P2 and V2 are the conditions after the change. So what we will do is just manipulate these equations algebraically, plug in some values, and just chug away to solve for what they're asking us to solve for. So if we look at this graph here, as the volume decreases from 1 liter to 0.5 liters, so we're starting to look here, 1 liter, and we're decreasing to 0.5 liters. We saw an increase in the volume. So pressure, I'm sorry, I misspoke right there. We saw a decrease in the volume and an increase in the pressure. So volume decreased, pressure increased. So we can solve problems now to determine what the size of, in this case, a balloon is going to be. So a balloon contains 30.0 liters of helium gas at 103 kPa. What is the volume of the helium when the balloon rises to an altitude where the pressure is only 25.0 kPa? And remember, for Boyle's law, we have to have a constant pressure. So we're going to write down what we know. P1 is 103 kPa. V1 is 30 liters. P2 is 25.0 kPa. So we see a decrease in pressure. And we're solving for V2. So we can set this up. P1 V1 equals P2 V2. And we're solving for V2. So we can rearrange this algebraically and say V2 is equal to P1 V1 over P2. Now we're going to plug in what we know. So we have 103 kPa times 30.0 liters. And that's going to be over P2, which is 25.0 kPa. When we multiply and divide this out, remember we go for our order of operations. kPa is going to cancel out with kPa, and we're left with a unit of liters. And when we multiply this through, we get 103 times 30 divided by 25, and we're going to go to 3 sig figs, so we have 124 liters. So what that means is when that balloon rose to that high altitude, where the pressure decreased to 25 kilopascals, the balloon is now 124 liters in size. So next up is Charles' law. As the temperature of an enclosed gas increases, the volume increases if the pressure is constant. So Charles' law states that the volume of a fixed gas is directly proportional to its Kelvin temperature if the pressure is kept constant. And now this part is very important. We need to make sure that this is going to be in Kelvin. The graph shows how the volume changes as the temperature of the gas changes. So if we look towards the beginning, or on the left-hand side, we see that the temperature is about 300 Kelvin and the volume is about 1 liter. And as temperature increases to 900 Kelvin, the volume also increased to 3 liters. So we can solve for these ones as well. So a balloon inflated in a room at 24 degrees C has a volume of 4.00 liters. The balloon is then heated to a temperature of 58 degrees C. What is the new volume if the pressure remains constant? And we have to remember that the temperatures must be in Kelvin. So V1 is equal to 4.00 liters. T1 is 24 degrees C, but remember we need that in Kelvin, so we're going to add 273.15, and that is going to equal 297.15 Kelvin. And then our V2 is what we're solving for, and T2 is 58 plus 273.15, so that's 331.15 Kelvin. So remember, this equation is V1 over T1 equals V2 over T2, and we're solving for V2, so we're going to rearrange this algebraically. V2 equals, and we can multiply the T2 to the other side. So we have V1 times T2, because we multiplied it over, divided by T1. So now we're going to plug in what we know. So we're going to plug in that 4.00 liters times 297.15 Kelvin divided by 330. I'm sorry, I'm getting mixed up here. So this is why we need to make sure that we pay attention, because now we have T2 on the top whenever we rearrange that algebraically. So we have 331.15 Kelvin on the top, and we have 297.15 Kelvin on the bottom. Our unit of Kelvin is going to cancel out, and when we multiply that through, we get 4.46 liters. So, as the temperature increased, the volume also increased. So now, another one of our laws was by the scientist Gay-Lussac. So this is Gay-Lussac's law. As the temperature of an enclosed gas increases, the pressure increases if the volume is constant. So Gay-Lussac's law states that the pressure of a gas is directly proportional to the Kelvin temperature if the volume remains constant. So there we have P1 over T1 equals P2 over V2. So Gay-Lussac's law can be applied to reduce the time it takes to cook food. In a pressure cooker, food cooks faster than in an ordinary pot because trapped steam becomes hotter than it would under normal atmospheric pressure. But the pressure rises, which increases the risk of an explosion. A pressure cooker has a valve that allows some vapor to escape when the pressure exceeds to the set value. Aerosol cans carry label warnings not to incinerate or to burn the cans or store them above a certain temperature. This problem will show why it is dangerous to dispose of aerosol cans in fire. The gas used in aerosol can is at a pressure of 103 kPa at 25 degrees C. If the can is thrown into the fire, what will the pressure be when the temperature reaches 928 degrees C? And again, here we need to remember that we need to be in the temperature of Kelvin. So for this equation, we have P1 over T1 equals P2 over T2. And they're asking us, what will the pressure be when the temperature reaches 928 degrees C? So we are solving for P2. So P2 equals P1 times T2 over T1. and we're going to plug in our values. So before we throw it into the fire, our conditions of P1 and T1 are 103 kPa and 25 degrees C. But remember, we need to be in Kelvin, so we add 273.15. So we are at 298.15 Kelvin. And on the top, we still have T2, and our T2 in Kelvin is 1,201. Should be 1,201.15 Kelvin. So again, the unit of Kelvin is going to cancel out. We're going to multiply this through and then divide by our denominator. And this can is now at a pressure of 415 kilopascals. So as the temperature increased, the pressure increased. So then we can throw all of these together. There's a single expression called the combined gas law, which combines Boyle's law, Charles' law, and Gay-Lussac's law. And that's P1 times V1 over T1 equals P2 V2 over T2. And if you think about these three equations separately, all we did here was just combine them all together. Because you can see Boyle's law, which is P1 V1 equals P2 V2. You see Charles' law, which is V1 over T1 equals V2 over T2, and then Gay-Lussac's law as well. When only the amount of the gas is constant, the combined gas law describes the relationship among pressure, volume, and temperature. So the only condition here is that we are not changing the mass or the amount of the gas. You can derive the other laws from the combined gas law by holding one variable constant, because then they will cancel out. The volume of a gas, let's try a problem. So the volume of a gas-filled balloon is 30 liters at 313 K and 153 kPa pressure. What would the volume be at standard temperature and pressure? Alright, so our combined gas law is P1 V1 over T1 equals P2 V2 over T2. And we are solving for the volume at standard temperature and pressure. So we have every piece of information except for the volume after the change. So we're going to be solving for V2. So let's do some algebra. V2 equals P1 V1 times T2, because we have to multiply it over to the other side. And on the bottom, we have T1 times P2. So that's our rearrangement. That's usually the trickiest part about these problems, just rearranging these problems. And now we have all these pieces of information, so we can just plug and chug. So again, we're solving for V2. P1, they give us 153 kPa times V1, which is 30.0 liters, times T2. In T2, our standard temperature is 273.15 Kelvin. And that's all over T1 times P2. And our T1 is 313 K times our standard pressure, but we need it in kilopascals, so that's 101.3 kPa. So let's look back through this. kPa cancels with kPa, Kelvin cancels with Kelvin. We're left with a unit of liters, which is great because that's what we're looking for. So when we multiply this through, divide by the denominator, we get 39.5 liters. So after the temperature decreased and the volume decreased, the volume increased. So in review, If the temperature is constant, as the pressure of a gas increases, the volume decreases. As the temperature of an enclosed gas increases, the volume increases, if the pressure is constant. As the temperature of an enclosed gas increases, the pressure increases, if the volume is constant. And when only the amount of gas is constant, the combined gas laws describe the relationship among pressure, volume, and temperature. One last thing here for a little bit more review, I wanted to put these equations here for you in case you missed them earlier. But these are equations that we're going to need to memorize and remember which one is Boyle's law, which one is Charles, Gay-Lussac, and the combined gas law. Have a good night, everybody. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, resources, CD, and pearsonchem.com.